Alright, today we're going to be doing something a bit different. We're going to be bashing math problems with programming. And since Olympiad problems, like proof-based problems, don't usually lend themselves to bashing, we're going to be doing mostly computational problems. So here I've compiled a list of problems from the AIME, which is the American Invitational Math Exam, which is a computational contest because it requires integer answers from 0 to 999. We're going to be doing some AIME problems using programming, and this is not how you're supposed to do them, but I just thought it'd be fun. So here we go. First up, we are going to be doing 2019 AIME 1, number 14. Okay, 2019 AIME 1, 14. And instead of doing this in my usual fashion, which is to record myself doing the problems and then explaining it afterwards, I'm going to do this live. So you're going to get to see my thought process. And these problems aren't going to be very hard to do with bashing. Oh. Wow. Okay. Find the least odd prime factor. Okay. I know how to do this problem. Actually, no, I don't. I know what the answer to this problem is, but we're going to be doing it anyway. And I know, like, 2019 to the 8 is a pretty big number, but I know the answer is small. Okay, maybe this isn't the best problem to do because I've done it before. So let's try a different problem. So we are not going to be doing this one. Okay, we're going to be doing 2019 AIME 2, problem 14. So here we go. Oh, okay. Hang on. Actually, I don't think this is a very good problem either. Yeah, I don't like this problem. Okay, we're going to be doing 2018 AIME 1, problem 11. Okay, this is good. Oh, wait. Yeah, this is a pretty easy problem to do. We're just going to be doing a lot of these because we can do them fast. So, here we go. Let's bash this. Okay, so find the least positive integer n such that when 3 to the n is written in base 143, its two rightmost digits in base 143 are 0, 1. So normally you'd solve this using number theory and like number theory skills, but we're going to be doing some bashing here. So first thing we do is set n equal to 1, and then while true, yeah, I'm using Python because I'm most familiar with Python. I know Java, but I don't really like Java, and those are basically the only two languages I know. I'm trying to learn C++, but yeah. Base 143. Okay. Huh. Okay, so we want to keep a mod, because since we're taking the last two digits, we're going to be taking a mod 143 squared, because that gives us the remainder, and which is basically the last two digits when written base 143. So 3 to the n mod right, of course. Okay, I always forget increment 195, and I'm pretty sure that's the right answer. Yes. Okay, so we have gotten it. So I'm gonna once we finish one, I'm gonna write it down. So yes, 195. Okay, so that was a pretty simple one. Let's do some more. 2017 2017, AIME 1, problem 11. Okay, this one's interesting. Okay, so consider arrangements of the 9 numbers 1 through 9 in a 3 by 3 array. For each such arrangement, let A1, A2, and A3 be the medians of the numbers in rows 1, 2, and 3 respectively, and let M be the median of A1, A2, A3. Let Q be the number of arrangements for which M equals 5. Okay. This shouldn't be that hard. We just have to import iter tools. Oh, okay, we have to save this as a py file. Py file. Okay, so we just have to import iter tools, and then we have to say something equals iter tools dot permutations. Here, let's search it up. Okay. Okay, we do not want Python 3.8. Okay. 2 point something. I am using Python 3.6 because TensorFlow only works in Python 3.6. Okay. So, permutations. Okay, yeah, this is good. Okay, we're going to do a length 9 permutation. And using this, we can find median. So, we're going to create a function which takes in the tuple and then constructs the array as well as finds the median of A1, A2, A3. So we might as well do a median function, right? Because okay, find median. So what we basically did here is we computed A1, A2, A3, and then we find the median. So yeah. Okay, now for array in K. Okay, hang on. If the median of A1, A2, A3 is 5, then we can increment count. Oh, oops, okay. Okay, so it should be 760. I'm a little bit doubtful about whether this is right. Okay. Yeah, we did something wrong. Huh. Okay. What? This is interesting. Oh, right, of course. It has to be 1 to 10 because we're not indexing from 0. Okay, and this gives us the right answer. The answer is 360. Whew. Okay. Next, problem 12. Let's see what it is. Hang on. I need to put the extensions on. Okay. So, call S product free if there do not exist A, B, and C in S such that AB equals C. For example, the empty set and the set 16, 20 are product free whereas the sets 4, 16, and 2, 8, 16 are not product free. Find the number of product free subsets of the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. We're going to need iter tools again. I think this might be a trend. We might need a lot of iter tools. So I think we're going to need combinations. We're going to need combinations. So okay, we're actually going to be using the numbers from 1 to 10. So we're going to do range 1, 11. And then, okay, we're going to have to choose all of them. Okay. Okay. Actually, no, wait. You know what we could do? We could use like a bit array. So yeah, we could do that. Yeah, I think that would make it easier. So that means we're going to do product. Actually, repeat equals 11 because we want to repeat equals 10 because there are 10 elements, and then from each of these we can for each of these bit arrays we can determine which elements are going to be included in the subset, and then from the subset we can just write this function. But first we're going to find a way to construct a subset from the bit thing. Bit thing. Okay. Okay. So I just want to make sure this works. What? Okay, we have done something wrong. Does it? Okay. Yeah, I think this is right. This is right. Okay. Oh, it did arrive at the end. Okay. Wait, but that's weird. Of course. Of course. Yes. Okay, so this is what we're looking for, right? Okay. And now we're going to write our function. So product free. So we're going to write a function to determine if a subset is product free. This is going to involve, you know what, we're going to make this a set because you can find if things are in sets much more easily. Oh, not necessarily distinct. Okay. And I'm sure this is going to work. There's only 1,000 subsets of 1 to 10. For each of those, it's going to be n squared. So we're going to have at most 100 times 1,000, which is totally fine. So, right. Also, I need to make sure to close out of these things. Okay. So we're just going to do a test of this function. So 416 is not. Okay, what about 2, 8, 16? False, good. What about 16, 20? True, okay, this is good. And if product free, $252. That's a weirdly round number because 252 is equal to 2 times 120 something. Okay, I'm too lazy to do this. 126. And 126 is 2 times 63. So it has a lot of factors. Okay, 252 is right. This is good. And now, okay, hang on. And now for problem 13. So, oh, also, I need to make sure these audio levels are going good because they often don't work. And because my microphone is like just sometimes really buggy. I mean, it's a good microphone, but sometimes it doesn't work. So let's do problem 13. Wow, look at all these real math solutions. Yeah, this is the way you're supposed to do math problems. But like, this is just for fun, right? So we're allowed to do this. Oh, we're already on 2017. Okay. Or are these all? Oh, these were all 2017. Dang. Okay. Okay. Great. Ah, God. Okay. I have to make sure to include these file extensions. Okay, problem 13. What is this? Is this AIME 1 or AIME 2? AIME 1, okay. Okay. Problem 13. Oh, yikes. Oh, yikes, this looks scary. Alright, for every m greater than or equal to 2, let qm be the least positive integer with the following property. For every n greater than or equal to q of m, there is always a perfect cubed k cubed in the range n is less than or equal to k cubed is less than or equal to m times n. Find the remainder when the sum over m equals 2 to 2017 of q of m is divided by 1,000. Huh. Okay, this is an interesting problem. I think we should start by defining q of m. So, least positive integer with the following property. For every n greater than or equal to, there's always a perfect cube. Oh, yikes. Okay, so this means n is going to be This means n is going to have to be large enough. So what this means is the cube root of n and the cube root of m times n. There's always going to be an integer in between those. That is the ceiling of the cube root of n and the floor of the cube root of mn. Yikes, mn. Okay. You know, this seems more like a math problem and not so much like a programming problem. But you know, I think we could just bash it. So we want to find if there's a perfect cube in the range n to m times n. And this means I mean, if we're summing over 2,000 integers, that doesn't give us too much wiggle room. So we just need to make sure that cube root. So here. Okay, hang on. Find integer root. Find cube root. Okay, well, you could do. Yeah, you could use binary search, but I am a bit befuddled, so we're going to wait, that's not right. Okay, that's about right. Wow, that is some precision. Okay, so let's see. Import math. We're also going to have to import math. So here we're going to find the cube root of m times n. And here we're going to find the ceiling of n. So we want to make sure this is greater than 1, because then we can fit an integer k in between. Then we can just return, wait, for every n. Oh, yikes. Oh, yikes. For every n. Oh, also I forgot to make this cube root. Every n. But like, if n is great enough, I mean, maybe not. Okay, what if we'll just verify this for like I mean, we could binary search it, but we don't have to, right? Yeah. This is not such an easy problem, but so for n in range, answer and plus, we'll just do like 10 verifications. And no, you can't see that. Oh, I should really be placing this on the left, shouldn't I? I mean, how easy is it to see the code? It doesn't cover up too much. It covers up a decent amount of them. So I'm going to put this on the right. Okay. I think that looks fine. Okay. Yeah, that looks good. Okay. So, okay, if this is, how about if this is less than or equal to 1, then we return false. Wow. There's got to be a breaking point though, because like we're not testing all n, so there's going to be some problems with this. So we'll try to compute also. Okay, this is weird. Does this make sense though? 2017. For every n greater than or equal to it. Perfect cube in the range. That makes sense, kind of. Oh. We might have to check really large numbers. Because cubes become sparser as numbers become larger. But, you know, it scales proportionally, so it should work. We'll just do answer plus m. Yeah, just to be safe, you know. So. Oh, okay. Well, that was pretty fast. 883. Let's see if this is right. Okay, nope, it's not right. Something is definitely wrong. What if we do m squared? Okay, this might be a bit difficult to compute. Is there anything that is wrong? Oh, it has to be strictly greater than. Yeah, that just means it has to be less than 1, not less than or equal to 1. And we don't have to verify all the way up to m squared. 159. Okay, it's not 159. I wonder if this is sensitive to like how many n's you check. So 205. Okay, yes it is apparently. Then I think this might not be the best problem for bashing. Nah. It's like no, it's not. It's not good enough. It's not good for bashing. So let's go back. Let's go back to 2017 AIME 2 and see if we can find more problems that are more bashable. Oh, wait, I think that does this already exist? Wait, which one was it then? It was AIME 1, not AIME 2. What? Oh, yeah. Okay, let's see if this problem's a bit more friendly. Friendly to bashing. 5 towns are connected by a system of roads. There is exactly 1 road connecting each pair of towns. Find the number of ways there are to make all the roads one way in such a way that it is still possible to get from any town to any other town using the roads, possibly passing through other towns on the way. Yeah, I think this is good. There are 5 towns, so in total there's going to be 10 roads. So 2 to the 10 possibilities. And then we can use some kind of DFS to see if a town is accessible by other towns. So here's an example. There's 10 roads Okay, that's going to be hard to describe. Oh man, okay. Okay, so it's going to be 1 if it's in the direction described, and if it's going to be 0 if it's not, or 0 if it is, and 1 if it's not. Actually, 1 if it is. 1 if it is. That just makes it less confusing. You know what? We're just gonna do this programmatically and not by hand, even though there's only 10. Okay, now we're gonna see. Is this thing? Yeah, okay, that works. Def works. Road system, I guess. Oh, okay. Okay, yeah. Okay, so all roads, perhaps. So what our plan here is we're going to be constructing that adjacency list, and then we're going to be doing a DFS. So okay. If I okay. If array I, this means this road is going the right way, then neighbors all I 0 yeah, that sounds right, and otherwise we'll just be doing the opposite thing. And now we're going to be doing the DFS. So yeah. So this is just a DFS right now. And yes. So if for any town it can't reach every other road, every other town, then we're going to return false. Otherwise we're going to return true. So let's see. False. Okay. We're going to be pulling out the iter tools again. Okay, and now $704. Okay, yeah, we did something wrong. Let's see. Okay, we did something wrong. Not sure what we did, but we will find out. Maybe it's the all roads. 15, 4, 1, 2, 1, 2, 1, 3. Yeah, that's right. But okay, something is clearly wrong. Okay, I'm sorry about that. This is okay, let's see. Okay, something is clearly wrong here. I think this might be a problem with how. Yeah, okay, I see why. Okay, so the problem here was that we were basically appending the same thing. Sorry, we were basically adding the same thing to the array 5 times. There were references to the same list. So if you add something to the list, it gets duplicated across all the elements because it's technically the same list. So I think we should get a, 544. I think that's the right answer. Right? 544? Yes, that is correct. Okay. Okay, now we're gonna do. Okay, sorry. Now we're gonna be doing our last problem, which is going to be 2017 AIME 2 problem 13. Oh, okay. This is kind of a math problem. Yeah, no, we're not going to be doing that one. 2016 primes. Actually, you know what? It's probably not that bad. This is going to be fine. This is 2017 AIME 2 problem 13. So, yikes. Okay, first thing. Okay, the important thing to note here is that we're going to be using iter tools again. And, oh yikes. Oh. This could get big. Let's try 30, choose 3. Okay, it's not that big. Okay, the limit here is on the size of the answer, because n, the sum of all n, can be at most 1,000. Because this is an AIME problem. So the answer has to be between 0 and 999 inclusive. So, yeah, this is definitely doable. This is problem 13. I think. Actually, you know what? I think this is more of a math problem, and I think it's actually pretty doable with math. So, we're not going to be doing this problem after all. Let's find another one. 2016 AIME 2 problem 13. Okay. I want an easy problem. Let's see. Problem 12 shouldn't be that hard. Okay, I think we can do this one. Okay. 2016 AIME 2 problem 12. Okay. The figure below shows a ring made of 6 small sections which you are to paint on a wall. You have 4 paint colors available to you, and you will paint each of the 6 sections a solid color. Find the number of ways you can choose to paint the sections if no 2 adjacent sections can be painted with the same color. I think normally you just do this with casework, and casework is made a lot better. Oh man, forgot to do the file extension again. Yeah, casework is made a lot better using programming. This is actually pretty trivial if you do it with programming, but it's pretty tedious if you do it by hand, I think. I mean, let's look at the solution. You're going to have to do a lot of casework here. Yeah, this... Okay, you could use generating functions. Yes, that would probably work. Yep, so there's quite a bit of casework here. Dot combinations. Combinations with replacement, right? No, it's actually product. It's gonna be product of 4 colors, and we're gonna be doing it 6 times. So because no 2 can be adjacent. Wait, this is actually a pretty trivial problem. I think the answer is going to be like... Okay, 732. I thought it'd be a lot smaller, but this is probably the right answer. Yeah, it's 732. Okay, so that concludes the solving math problems with programming video. I might do more of these in the future, but I don't know. I think that was pretty fun. If later I probably want to spend more time on this, and I don't know. This seems pretty fun. You know what makes me sad or like a little bit disappointed is that you can't really solve Olympiad problems using bashing. But maybe that should be how it is. You probably shouldn't be able to bash Olympiad problems because they're supposed to be about problem solving, you know? And like, so are programming problems because you can't just bash a programming problem because you know you have time constraints. The thing about math problems though is that the numbers are always really small if it's like a computational problem. If it's an Olympiad problem, you might have to deal with an infinite number of numbers. But with computational math, it's usually pretty finite and also like not very big numbers, so you can probably calculate it in enough time. And also you don't have time constraints, so if you need a minute, you can just use a minute, whereas on a programming competition, you can't take a minute. That's way too long. But then again, like, if your thing's gonna run like not in time, it's probably like gonna run really not in time. Like if it's gonna take over a second, it's probably gonna take something like 10 days or something, because think about it, if you have a test case which has n equals 10 to the 5, you're gonna have to make that what? And if you have an n squared algorithm, that's gonna be 10 to the 10. 10 to the 10. And if you assume 1 second, okay, that's probably not true. 10 to the 10, that's gonna be 100 times 10 to the 8, right? Okay, that took me a long time to figure out. 100 times 10 to the 8, if you assume 10 to the 8 can run in 1 second, that's gonna be 100 seconds. Okay, that's not too big. But I mean, for like maybe other problems or something, 100 seconds is pretty long. But okay, yeah. So I guess I was wrong a bit. So yeah. Well, I hope you enjoyed solving these math problems with programming, bashing them out. I'll take a look at some of the problems I didn't do, And yeah, I'll probably make a separate video if you know that's something that is desired. I think it was pretty fun, but I only like doing the easy problems because it makes me feel better. Okay, well, I guess it's time for the video to end. And I'm not going to edit it, but maybe the next one I will edit if it's going to be a better video. So thanks for watching, and I'll see you later in tonight's LeetCode contest. Goodbye.